This video is going to be all about how we determine which antibiotics an organism is susceptible to and how we determine the minimum inhibitory concentration, which is the smallest concentration of an antimicrobial that visibly inhibits growth. And that's important because you want to find the smallest effective dosage, right? Because our goal here is selective toxicity. You want the drug to be potent enough to harm the target, the bacteria, but not potent enough to cause serious side effects to the host. So we're going to talk about the Kirby Bauer technique, which is going to tell us which drugs may be a good one to use to combat an infection. And then we're going to talk about the two dilution tests, which is what helps us determine the MIC. So this is the Kirby Bauer technique. And how it works is you take an agar plate and you use a swab to cover the plate in the pathogen that you're trying to figure out how to beat. Okay, so maybe you take a sample from a patient or something like that, and you're going to swab it all over this plate to create a lawn of bacteria. Then you take different discs that have been soaked in different antimicrobials, and you place the disc on the bacterial lawn, and then you place it in an incubator for 24 hours. And when you remove the plate the next day, you'll see something like the one shown in the top right. And so what you're looking at here is you want to see if the drug had any effect on microbial growth. And so for two of these antimicrobials, this one and this one, right, the drug had zero effect on the bacteria. And you know that because the bacteria grew right up against that disc. Those antibiotics didn't slow it down at all, okay? But for the other 5, for the other 5 antibiotics, there was some inhibition. Now, we can't tell if the drug actually killed the organism or just prevented those initial cells from growing. We just know that they were not able to replicate a lot overnight. And so those clear zones that you see are called zones of inhibition. And they form because the bacteria is unable to grow in the region surrounding the disc. And what happens is this disc has been soaked in an antibiotic. And so over time, the antibiotic diffuses outwards onto the media, onto the plate, okay? So at the area right around the disc, there is a lot of antibiotic, okay? Those up arrows are trying to say there's a lot of antibiotic. But as you go farther and farther from the disc, there's less and less antibiotic. And so right here at the border, that was the amount of antibiotic that was able to kind of keep the bacterial growth at bay. But any less than that, the bacteria could grow just fine, okay? And so we're going to talk a lot more about this technique later in this semester. So for now, we're just kind of doing a big picture overview. But a zone of inhibition itself is not enough to indicate that the bacteria is susceptible to the drug. You actually have to measure the zone in order to figure out if the bacteria is susceptible or resistant. And sometimes there's even an intermediate effect, but what you really want if you're trying to help a patient, right, is to find a drug that the bacteria is susceptible to. And so researchers figured out what size zone is required to actually indicate whether or not a bacteria is susceptible or resistant to a drug. Because again, remember, there's a ton of the drug right around the disc. And so maybe that's not actually how potent of a drug you would give to a patient, right? And so you need to know if the zone, like where it ended, is actually kind of comparable to how much of the drug you would give to a patient. And so let's pretend this guy right here is erythromycin. And we measured the diameter of this zone, and we found it to be 20 millimeters. Well, you would look right here where it says erythromycin. We would say, okay, we have 20 millimeters. Well, that is larger than 18, so the bacteria is in fact susceptible to erythromycin. But now maybe we're looking over here, and let's pretend this one is neomycin. And we're going to pretend that zone of inhibition is 5 millimeters. Well, we would go over here to neomycin, and we would say, okay, where does 5 fall into play? Well, 5 is going to be less than 12, so this bacteria is actually resistant to the amount of neomycin that we would give to a patient. Okay? All right, so next up, let me clear this slide, sorry. I had just recorded this video, but with no sound, so I apologize. Let me see if I can get this to go away. Oops. Oh, it's not letting me. I'm sorry. I don't even know what's happening anymore. There we go. Well, it's okay. I'll just talk around it. So for the antibacterial dilution test, this is the test that's going to help us determine that MIC, the smallest effective dosage that you would want to give a patient. And so what you do is you have these test tubes that all have nutrient broth in them. And then you would add a certain amount of the antibiotic to each tube. So notice on the left, we added 2 micrograms per mil of the drug to the test tube, and then we add more and more to each tube. Then you add bacteria to the broth, and you stick it in the incubator overnight. And when you take out the tubes the next day, you look to see where there's growth. So the 2 tubes on the left, those dosages are too low to be helpful to a patient, because look how much bacteria grew even when that drug was present. So we know that's not a potent enough concentration. But 8 micrograms per mil was just enough to prevent bacterial growth. So that would be our MIC. Okay, so there's no need to, give your patient 16 or 32 micrograms per mil when 8 is sufficient. Okay, and so our MIC here would be 8 because no growth occurred at that concentration of antibiotic. Now you can do this on a larger scale with this, it's called a 96 well plate because there's 96 little wells in there that you can add media to. And so that's essentially what they did. So they put the broth and stuff in here. They added different concentrations of erythromycin. So the lowest concentration is on the left. The highest concentrations are on the right. You'll notice they added penicillin to a different row and clindamycin to a different row. And then they added the bacteria to each of these wells, and they incubated it. And then when they take the plates out the next day, they can see where no growth occurred. And so you can see that with the little red circles with erythromycin, penicillin, and clindamycin. So they can figure out what that MIC is. All right, y'all, that's the end of this video.